Okay, let's unpack this. We spend so much time talking about, the massive scale and billions of parameters in these foundation models. But what happens after all that expensive training is done? I mean, the core challenge for almost every real-world AI application is figuring out how to make these systems smarter, more reliable, uh, capable of adapting to new rules or situations without the nightmare of constant, really costly retraining.
That really is the frontier, isn't it? We're definitely moving beyond the idea that performance is just, locked into the model weights. The key shift, and I think this is becoming a central paradigm, is context adaptation. So we're talking about modifying the inputs themselves. Things like the instructions we give it, maybe evolving memory, the factual evidence that gets fed right into the LLM's prompt at inference time.
Right. And this framework we're diving into today, Agentic Context Engineering, or ACE,
Yeah.
it treats this input context not just as like static instructions, but as an evolving playbook. It sounds like we're giving the AI a custom living manual for every situation it faces.
Precisely. And the goal here is really flexibility and efficiency. When you adapt the context, instead of messing with the model weights using things like LoRa or full fine-tuning, you get some massive advantages. For one, contexts are immediately human interpretable. You can actually look at the playbook and get a sense of why the AI made a certain decision. They also allow for really rapid, runtime integration of new knowledge. And they can be shared instantly across different modules within a more complex AI system. Think system prompts, detailed memory structures, factual evidence. This approach really underpins making AI scalable and, crucially, self-improving.
Okay, so if adapting the context seems like such a clear win, what were the big problems? What are the fundamental flaws in the older methods that ACE is specifically designed to fix?
Yeah, our sources point to two really significant problems that current prompt optimizers and adaptive memory systems tend to bump into when they try to manage context. The first one is something they call brevity bias.
Brevity bias. That sounds almost counterintuitive. Why would being concise be a bad thing? Don't we usually want short prompts?
Well, yes and no. The issue is that previous optimization techniques really strive to generate the shortest, most concise, sort of broadly applicable summary possible. They operate on the assumption that brevity equals efficiency. But in really complex real-world tasks, think about multi-step agents trying to navigate software interfaces or maybe specialized legal or financial analysis, that brevity often means sacrificing really important detail. We're talking detailed, domain-specific heuristics, precise guidelines on how to use tools, or even hard-won knowledge about specific failure modes you want to avoid. That stuff gets lost.
Ah, okay. And this is where the AI kind of diverges from how we learn as humans, maybe. Like, we benefit from a concise generalization that five-word executive summary is useful for us. But the research suggests that LLMs often perform better when they're actually saturated with long, detailed context. It seems they can figure out what's relevant on their own during inference. So preserving that comprehensive detail might actually be better than aggressive compression for them.
Exactly. Which brings us neatly to the second, and frankly, much more dramatic limitation: context collapse. This is what can happen when adaptation methods rely on the LLM itself to monolithically rewrite the entire context over and over again as it learns new things.
Monolithically rewrite. So the LLM is basically given the job of editing its own memory, and it gets a bit too aggressive with the delete key.
Not just aggressive, sometimes it's actually catastrophic. We saw a really stark case study on the AppWorld benchmark, which involves pretty complex interaction sequences. An agent had successfully built up this detailed context. It was about 18,282 tokens, and it achieved a decent accuracy, 66.7%. Then, in the very next adaptation step, the LLM was tasked with rewriting that entire context. It just aggressively collapsed all that information down into a summary of only 122 tokens.
Wow. Wait, from over 18,000 tokens down to just 122 in one step. That's like trying to summarize a massive textbook into a single tweet. What did that do to the performance?
Performance just plummeted. Accuracy fell sharply to 57.1%. And here's the real kicker: that 57.1% was actually worse than the baseline accuracy of 63.7% the model achieved without any context adaptation at all. The compression actively destroyed its ability to do the task.
That is fascinating and, yeah, a bit alarming. It's almost like when I try to clean out my notes app, summarizing a trip itinerary, and I delete the crucial flight number because I thought just the destination city was enough detail. The whole point of the detail gets lost when you overgeneralize.
Precisely. Domains like interactive agents or complex financial modeling, they depend on retaining that detailed, task-specific knowledge. You absolutely need a system that accumulates knowledge effectively, not one that collapses it into useless, broad generalities.
Okay, That sets the stage perfectly for ACE then. If the older methods fail because they try to summarize everything away, ACE's philosophy must be about keeping everything, but keeping it organized and useful.
That's exactly the breakthrough idea. ACE positions context as these comprehensive, evolving playbooks that accumulate and organize strategies over time, rather than just being condensed summaries. And to handle this complexity without getting overwhelmed, ACE uses an agentic architecture. It's somewhat similar to predecessors like Dynamic Cheat Sheet, which itself is a framework for using LLMs to synthesize strategies, but ACE imposes a much more rigorous and structured division of labor. It involves three specialized components, three distinct roles.
Okay, walk us through that modular workflow. How do these three agents, these roles, interact to build and manage this playbook?
Right, so first you have the generator. This is your core task solver. It's the agent that produces the reasoning trajectories, tries to solve the actual problem, whether that's generating code, answering a question, navigating an app. Second, you have the reflector. Now, this component is absolutely critical. It critiques the generator's execution traces, it diagnoses the specific errors, and it extracts concrete, actionable insights from both the successes and the failures.
Got it. So the reflector is like the critical self-assessment layer, the coach reviewing the game tape, and then who actually updates the playbook based on those reflections?
That's the third role, the curator. The curator synthesizes all those lessons learned by the reflector into structured context updates. It essentially manages the evolution of the playbook. And this modularity is really key. It prevents overloading a single model with too many conflicting responsibilities. Trying to experiment, reflect, and consolidate all at once. That often leads to pretty poor outcomes.
So the real innovation here, the thing that prevents that catastrophic context collapse we talked about earlier, must be how the curator actually updates the playbook. If it doesn't just rewrite the whole thing, what's the mechanism?
You've hit on it. The first key innovation is what they call incremental delta updates. Instead of treating the context as one giant monolithic blob of text, ACE represents it as a structured collection of itemized bullets. Think of these as specific strategies or concepts or known failure modes. And each bullet has associated metadata, including counters that track how often it was helpful or maybe harmful during past executions.
Okay, so it's like having a digital checklist or maybe a card index where you only update the specific bullet points or cards that changed or gain new metadata. You're not rewriting the entire page every single time you learn one tiny new detail.
Exactly. The curator produces these compact delta contexts, just small sets of new or updated bullets. And these are then merged deterministically using lightweight, non-LLM logic.
Okay, help us unpack that phrase, non-LLM logic. Why is that distinction important?
It's really important because it addresses cost and speed directly. It means we don't rely on another complex, expensive, and potentially slow LLM call just to perform the merging operation. Instead, ACE uses simple, reliable code. Think of it like a basic copy and paste function, but with predetermined rules to combine those delta updates with the existing context. This avoids the cost and the high latency you get with full rewriting, and crucially, it prevents the LLM from accidentally collapsing essential knowledge during the update process.
Makes sense. And presumably, to make sure this playbook doesn't just grow into an unmanageable mess over time,
No.
there needs to be some kind of maintenance.
Yes, that's the second key innovation, the grow and refine mechanism. This balances the expansion where new bullets are simply appended to the list with active maintenance. So existing bullets can be updated based on new feedback, and there's a crucial process called semantic deduplication that's used to prune away redundancy.
Semantic deduplication. Can you give us a quick, concrete example of what that looks like in practice? How does it know two things are redundant?
Sure, so the system might identify two bullets that, while worded differently, essentially contain the same core strategy. Let's say one bullet reads, always use tool A first when encountering a directory structure, and maybe another slightly older bullet reads, start the task by initiating a call to the directory parsing utility. The system, often using embedding similarity or maybe another lightweight check, recognizes these are semantically very close. They convey the same fundamental instruction. It can then automatically merge them or just delete the redundant entry. This keeps the context relevant and manageable without letting it just bloat endlessly over time. So what does this structured agentic approach actually deliver in the real world? I mean, the proof is really in the numbers here. ACE consistently outperforms strong baselines across multiple types of tasks. We're seeing average gains of about 10.6% on agent tasks and 8.6% on these specialized domain-specific benchmarks.
Let's focus on that agent case study for a second, because this finding has potentially huge implications for the industry. You mentioned the AppWorld benchmark, which is known for being really tough in multi-step planning. And the sources show ACE was tested using DeepSeek v3.1, right? Which is a smaller open source model.
That's correct. And despite using this smaller open source model running the React framework, but augmented by ACE, the system was actually able to match the performance of the top-ranked production-level agent on the overall average score. And that top agent, called IBM CUGA, was powered by the highly advanced proprietary GPT 4.1 model.
Wait a minute. Let me make sure I heard that right. You're saying a smaller open source model, simply by having its context playbook optimized by ACE, managed to match the performance of a proprietary state-of-the-art model like GPT 4.1 on a highly complex task. Well, that's remarkable. Why do you think context engineering gave it such a disproportionate boost?
It really seems to boil down to the depth and complexity of the task. When tasks involve multiple turns, specific rules, dependencies between steps, which is exactly what AppWorld tests, having that precisely curated, comprehensive playbook of strategies, which ACE provides, seems to compensate significantly for any potential deficiencies in the base model's raw knowledge or scale. Essentially, the context guides the reasoning trajectory much more effectively, step by step.
And it gets even better, apparently. On the harder test challenge split of that same AppWorld benchmark, the React plus ACE implementation actually surpassed the proprietary model. That feels like a really clear demonstration that for certain complex multi-turn reasoning tasks, context depth can actually trump raw model scale.
Absolutely. And what's more, it achieved this self-improvement without requiring expensive ground truth labeled supervision. It managed to leverage natural execution feedback, things like whether it generated a piece of code compiled successfully or failed to update its own playbook effectively.
Okay, so beyond agents, you also mentioned domain-specific knowledge. Where else did ACE show strong results?
Yeah, it showed really strong improvements on specialized knowledge tasks as well. Examples given were finer and formula, which involve complex financial reasoning based on XBRL data. For listeners who might not be familiar, XBRL is basically the standardized language for electronic financial reporting, so quite technical. This confirms that ACE's ability to construct these detailed playbooks with precise, domain-specific concepts isn't just limited to agents. It's generalizable across various knowledge-intensive, often regulatory applications.
And here's where, the rubber meets the road for businesses implementing this stuff. The efficiency gains. By avoiding those catastrophic monolithic rewrites we discussed, ACE seems to drastically cut the operational overhead.
That's right. The sources show an average of 86.9% lower adaptation latency compared to existing adaptive methods. Well, that's a game changer, especially for continuous learning scenarios.
Why is that latency reduction so critical, especially for systems that learn online, as they say?
Well, think about it. If your adaptation process takes too long, you simply can't integrate new knowledge or feedback in anything close to real time. A slower system has to batch up its updates, which means it's operating on potentially stale knowledge for longer periods. When ACE was compared directly to dynamic cheat sheet, which is another known technique for adaptive prompt engineering in an online setting on that finer financial task, get this. ACE achieved a 91.5% reduction in latency, and maybe even more impressively, an 83.6% reduction in token dollar cost.
Wow, nearly eliminated the cost and the time required for adaptation. That really is the difference between a sluggish system that needs scheduled batch updates overnight and a truly continuously learning agent that can adapt almost on the fly. That's a massive competitive advantage in fast-moving domains.
And if we connect this to the bigger picture, context adaptation done this way is just fundamentally cheaper than updating model weights. Updating those billions of parameters through methods like LoRa or fine-tuning still requires significant computational resources, time, and data. ACE, by contrast, offers this flexible, really efficient alternative for continuous learning. It allows systems to rapidly adjust to things like data distribution shifts, or maybe incorporate new rules and regulations without ever needing to touch the underlying foundational model weights.
Plus, there's that critical benefit of interpretability you mentioned earlier. If the context is basically a human-readable playbook, that opens doors for governance, for compliance, right?
Oh, absolutely. Because the contexts are itemized and human interpretable, it facilitates something really important called selective unlearning. A domain expert can actually go in, identify, and remove specific outdated or incorrect information, a bullet point, essentially. This is becoming crucial in highly regulated fields. Think about compliance with requirements like GDPR or CCPA, where the right to erasure or data correction is legally mandated. You can scrub a single bad strategy or piece of data from the playbook almost instantly. Compare that to the near impossible task of trying to retrain or refine-tune a massive model to make it forget one specific detail reliably.
That's a really powerful capability. It raises an important question, though. The whole system seems to depend critically on extracting high-quality lessons via that reflector agent. What happens if the input quality is poor or the feedback loop isn't clear? Is there a failure mode here?
Yes, and that is the critical caveat mentioned in the research. ACE's performance is indeed heavily dependent on the quality of the feedback it receives. If reliable supervision, whether that's clear ground truth labels or unambiguous execution outcomes like code success failure, is absent, the system can really struggle. In those situations, the context can actually become polluted by spurious or misleading signals from the environment. If the reflector agent can't extract meaningful, correct insights from the feedback, then the curator might add useless or even harmful bullets to the playbook, potentially causing performance to degrade over time.
Right, so the old adage, garbage in, garbage out, still very much applies. That reflection layer has to be robust and accurate. It needs to identify meaningful lessons that genuinely lead to better outcomes.
Precisely. AC is going to be most beneficial in scenarios where there is rich, reliable feedback readily available, like observing whether generated code actually runs or if an API call succeeded or failed. That allows the reflector and curator to make sound, high-fidelity judgments about which strategies truly work and should be reinforced in the playbook.
Okay, well, we've covered a lot of ground. We looked at the limitations of previous context models like brevity bias and context collapse. We unpacked the elegant agentic architecture of ACE with its generator, reflector, and curator. We dug into the modular innovations, those delta updates, and the grow and refine mechanism that prevent collapse. And we saw the staggering performance and efficiency gains, especially that example where an open source model managed to punch far above its weight class.
It really makes you think, doesn't it? If context adaptation, done well, can enable a smaller, open-source model to actually outperform a state-of-the-art proprietary giant on challenging multi-turn tasks, does the future of AI system improvement lie less in this relentless drive for continuously scaling model size, and perhaps more in perfecting the art of structured, adaptive context engineering? It prompts the question for anyone listening: what specific domain knowledge, what nuanced strategic rules from your unique field could you distill into a comprehensive playbook to significantly boost an LLM's performance on the tasks you care about? That's really the personalized knowledge revolution that ACE seems to enable.